We are going to have a live demo, so if you want, you can just start opening your laptops for later. We hope that it works. We are not fully explaining it works because there are lots of people here and the network might be packed. But let's see how it goes. So my name is Oak, I'm from Topology, and we are talking here today about CRDTs. Who here knows CRDTs? Ever heard about them? Some people. Not many, but some. Okay, it's good then. And a new concept that we are building at Topology, which is config-free replicated objects, which is basically composable CRDTs. So, CRDTs in a nutshell. CRDTs are based on a paper which is config-free replicated data types, and basically they want something super nice, which is cool stuff. Basically, what CRDTs allow us is to have monotonic data types, so data types that only grow, and because they only grow, we can change them in different computers we don't care about where we are changing them, and when we merge, we expect them to merge without having any conflict, which is something super awesome, because lots of times in blockchains we are thinking about, oh, how can we achieve consensus, and consensus has lots of problems, we introduce lots of bottlenecks, and having some other types of distributed systems that allow us to have stuff without consensus is super nice. So some of the main examples that we have for CRDTs. The first two are the most basic ones. The last one is a bit more trickier. But basically, the first one is a grow-only counter, which is I'm incrementing my counter here alone, totally fine. Anyone else is incrementing their counter, and when we merge, we are just picking the maximum of both counters. And we know that the counter is going to be always not smaller than my own local version of the counter. So if I'm incrementing, if my counter is already incremented by 5, I know when we are fetching the latest state, it's not ever going to be under the 5. The thing that also enables us is to have positive negative counters. And there we are already adding a new variant, which is we have the two grow-only counters, one for positive values and one for negative values. The thing is, when we want to have the value of the whole CRDT, basically we just subtract one by the other. We subtract the positive counter by the negative counter. So we can also always have a local state that is true, always. And when we merge it, it might be different the ultimate value. We don't ensure that it's bigger or smaller, but we know for sure that the counter for the positive values and the counter for negative values are never going to be less than our local version. Another example that it's way more complex is JSON CRDTs, and these basically are constructs with lots of smaller CRDTs that enable us to do something like it's JSON compatible. So we start interacting with like objects and stuff like that. Any cool. So in Topology, we already did some past experiments with the CRDTs. The main experiment that we did was Penguin World. It's just penguins hopping around in a super platform game. Not game, because we don't have a goal here, but we could shoot some snowballs and jumping. We had collision here, which is something that is trickier when you are doing it in a peer-to-peer fashion. And it was awesome. It was built with something that it's missing there, but we made a tweet about it and we got some good reactions from other nice people also, and people were super hyped about this. So the thing, I'm going a bit back because it seems that it's missing here the dependencies that we use, but basically the dependency that we mostly used for building the Penguin world was YGS, which is a library that is super known for CRDTs. We also used WebRTC, and that was more or less implemented by us according to the standard. We did the STUN protocol, which is something that allows you to exchange some session description and then you can have direct connection between browsers. And we used Phaser for the platform itself for building the game. And fast forward, after all that, YGS is super nice, WebRTC is super nice. It's tricky to implement, but it's also super nice. But we decided that we wanted actually to build a protocol around it and abstract a bit the kinds of config-free replicated objects that we can have. And that's where we started defining the topology protocol. And basically the CROs that we are here talking a lot about, it's something that already exists for quite a while within the programming space, which is, we have Smalltalk, which is a programming language that is pretty old. Who here knows about Smalltalk? The same people that know about CRDTs, okay. okay, we are aligned then. So, but the thing that Smalltalk objects allow us to do is, they allow us to do lots of things, and the thing is, we have blueprints for those kinds of objects. We have the state definition, so basically the CROs that we are talking about are composed by some kind of state, and then some functions. Those functions can be views or can be mutators, so they can mutate state actually. The thing about the mutation is it's monotonic, so we can only grow in size. The nice thing about it is when we are talking about mutators and views as functions, we can actually do that in any kind of programming language that we want. We can have any VM that we want. We can have JVM for Java. We can have WASM. We can have Solidity, the EVM. We can have Cairo VM. We can have everything that we want there. So it's actually, we can integrate that into the VM, and the only thing that we need is computate the state and then do the merges and the updates on the state. Here at Poji we decided to go straight forward with WASM because WASM is the most known VM that is working in WoW, that is compatible with other weird environments. So currently we are handling it with WASM. We don't have that yet, but soon. You just need to wait a bit. And the thing is, those CROs also support signaling. So the thing is, we actually don't want to have everyone in the network to know about all the CROs that exist on the network. It's not going to scale. It's going to fail totally. And the thing is, we have to have a way of signaling between those objects for people that don't know about each other on different parts of the network. And that's something that we are also building, incorporated within the objects themselves. And here the merge function is the thing that we have in CRDTs all the time, which is when we go apart from some time, then we need to merge states. Those can be based on operations, or it can be based on the state itself. So this is a bit outdated, but here we have a broad scope on what we are talking about in 2 months ago, maybe 2 months. So here we have lots of stuff outdated, but there are lots of stuff here that it's still useful for us. So one thing that is important is the peer-to-peer messaging. Currently we are holding it with P2P. Everyone knows it? That one is using Ethereum, the IPFS and all that. You should know that one. So we are using it with P2P for causal consistency. That's super important when you want to have history on the operations that you did. And for that you want to have actually a causal relationship between all the operations that you are making. And for that we are planning on using hash graphs and all that. And consensus. Consensus is a super nice one because we talked in the beginning, it's like, oh no, we don't need consensus. And suddenly it's like, consensus there? And the reason for that is from time to time, so since the state is grow only, we actually need to purge state. As otherwise you are going to spend lots of RAM storing those kinds of objects. And the thing is, for us to do those types of compaction of the state, we actually need a consensus on some timeline saying, yeah, so everything that appears that is as a dependency before this, we just ignore that. We are not using that. And that's why, the thing is, this is totally new and we are still highlighting how are we going to do this, but these are more or less the guidelines that we are thinking about. More than happy to discuss it with anyone after. Basically, that's what I was, here is the super nice sketch with, like a kid did. And the thing here is the definition of the peer-to-peer network that I was talking about. So if we define as all the objects with those colors, we don't want everyone to store all the objects. We want some people to store some objects, and one application can be composed by many objects, actually. They don't require us to have just one. So, and the thing then is we can have signaling between them and interacting within each other. Use cases for this. Collaborative tools, this one is, CRDTs are the most used on these ones currently. So the collaborative tools, you can think about Google Docs. So when you are changing some document, you are adding changes. Actually, old times, people used something which is called OT. I don't know if anyone knows it. It's operational transforms, and nowadays people are using OT and CRDTs to do those kinds of stuff. Local first software, which is the concept of you can have your local version of your software, you do everything that you want there, and the thing is, you just synchronize when you go online. So when you are doing it on your computer, you can be offline, you know that the state is going to persist and it's going to be super cool. That's nice. Then we have social networks and social applications. Here we have a big example, which is Forecaster. Forecaster is actually using a big CRDT to store all the posts and all that. Then we have games and autonomous worlds, which is usually our main example and the main use case. It's our examples are usually done within those, and that's a big use case that we have there. One of our main goals is FPS, right? First-person shooters. We can do that. Wait 1 second. And now it's the time for live demo. Let's all cross fingers and hope it works. You can join. I didn't put a QR code because I don't want you to join with mobile. Mobile is going to break for sure. But you can join there with counter-splash.topology.pg. And I'll also join and let's see if it works. Now is the time that we are trying. Yeah, you can just see my bookmark, it's fine.
Oh, I see people.
You see people?
Yes, I see bubble thing jumping around.
Oh, I need to change my way out, by the way. So if you use QWERTY...
Oh, I see multiple bubbles.
Someone died.
So the purpose of it is that you need to find the route to go to the canvas and then start painting.
So here I can already show you the shortcut.
Let's see.
Alright, so if you find the map that is too hard and all of that, you can blame Mujan. He's somewhere there. And he was the one that did this. And here, you need to pick a good sticker.
No.
And here, we have good stickers there. So basically this is demo. We have some balls there, so anyone that tried probably is there. They
What happens if you die?
If you die, just restart it. It's like here. So here, we are back here. Yeah. So it seems that some people are jumping, so it's nice. We had some connections, it seems. Even if the network is not that good, it works. I'm dropping off from here, but you can just keep jumping if you want, and come back here. Okay, nice. So that's our super live demo. It worked. This was the backup, by the way. we had a backup plan. Already with the wall full of stickers and all that, we had a backup plan. And now it's the reason why we needed a backup plan. And the thing is, we didn't. We had success. We are super good, and the gods of the internet make it happen. So it was good. But actually, there are some failure scenarios here that we might have encountered while testing here. Mainly, the most problematic ones is firewalls and data traversals. And then you could bypass that using relay servers and all that. The thing is, actually, the kind of data that we are passing by, it's kind of a lot, and relay servers, if you are having lots of connections to those relay servers, they can't handle those. It's basically not feasible. The thing is, here we have a way of bypassing this in some way, which is actually having some node that has public connection to everyone. And if you have that, you might, if you are an application with lots of traffic, you might want to have more than one. But just having someone that is there and can, so most of the communication that we are doing is PubSub. I don't know if you know about it, but basically someone subscribes to some topic and then receives and listens to all of those topics. And because of that, if you have some public node, it can just relay all the messages all the time. So that works actually. We didn't implement it here, but it still works, so it's fine. And then for gaming in special, so Penguin World was fantastic. It was not BFT at all. So Penguin World, you could just start teleportation. You can actually move other players. Because the way we were doing collisions was, we were trying to collide two objects and then it's like, oh, you should back off this amount because I collided with you, and I sent that message to the guy, and he was like, okay, I'll back up. No worries, I'll back off. And the thing is, doing that, you can actually make other players move by a lot. And the thing is, these are problem. You also have SpeedX, but that's a problem in most of the games, always. And the thing about teleportation, telekinesis, and all that is we actually need to have invariants within the objects and all that, and we need to find those in order for us to solve those kinds of problems. And that's actually what we are doing at Topology. We are solving lots of our problems in distributed systems. So we have the part of the constraints in CRDTs that's super new. There are some people working around it nowadays in PhDs and all that. In Portugal, they are doing that. We also have clocks and time. It was always a problem in distributed systems. We usually use vector clocks, thresholds, logical clocks that you have dependencies on the. So your clock is not a timestamp. It's basically is when some operations has a dependency on another operation, we know for sure that that operation happened before. Compaction, we already go through it a bit. Hash graphs also, and other super cool problems in distributed systems. And because of we are working on lots of those, and we are kind of short-handed. We have open position, so if anyone is interested in these problems, you can just reach out to us, and we are more than glad to talk with you about it and all of that. If you are not interested in those kinds of problems, and you just want to hang out for the vibes, yeah, we can also have lots of communication channels. We have our website, we have the Discord. So this QR code here is for the Discord, actually. Because the link is a bit tricky. So you can also boost the server for us to have a nice link. We also have the GitHub. Most of the stuff that we are building is open source. We have our paper there, which is a bit updated. We are going to update it within the next week with the latest stuff that we are doing. We have the specs there. We have all the codes for Countersplash, all the codes for the 4G protocol itself. And then you can also follow us on Twitter for listening out where we are going to be and where are we going to talk. And basically that's it. Yeah. So we still have lots of time, so you can just ask questions now. If
I have a question. So in this case, each game, it's a game for itself. Like there's no ranking, like there's no state that is stored somewhere.
So the states are usually stored within the client, yes. And the thing is, the state is shared. So if you are a game developer and you want to have a global state and all of that, you have two ways of doing it. You can do a semi-centralized version of your game, where part of it is a CRO, part of it is your centralized thing. But if you want to do it fully decentralized, everyone is going to keep the chain. And the thing is, you run one or multiple nodes where you are going to have the state there also.
Mm-hmm.
Yes.
I see.
So I'm just trying to wrap my head around it.
Yeah.
But you said, well, the weaknesses, right? There's telekinesis. There's
those are
if you just use it, if you just use it as is, you can very easily do all kinds of hacks and do things on behalf of other players.
No, you can't, because you have public key encryption, so you can every message that you are sending to the network, you're actually signing it, and you have a node ID.
Okay.
So actually, you can't say that you are another person and you want to move that position of that player. No, for you to have that kind of operation, you need to sign that operation.
Okay, so they're authenticated. So
Yeah.
Okay.
Yeah. There are, those kinds of problems are totally feasible, but the thing is, those are also easily fixable. So with cryptography, you can fix those easily.
Right.
Yeah.
I mean, the main issue is the writing history, right?
Rewriting history, it's actually because those operations are going to be validated by the other peers also in the network.
Yeah, but then if you make a lot of peer and you attack and you
But if you sign all of those and everyone says if you have a Byzantine network, it's the same as blockchains. If you have 60% of the nodes that are bad, you can.
Yeah, but here it's cheap.
Huh?
Here it's cheap.
Here it's cheap. It depends because it depends on how invariants are created. Because you can actually make as the invariants don't allow certain actions by certain players, or you can have limitations on the actions. Like if
But you can create many players.
Yeah.
I mean, you are like the only solution is to make a blockchain in the end.
Not necessarily. A blockchain is not going to solve it also.
I mean, the main issue is DDoS, right?
Yeah. That's always a big issue in peer-to-peer networks. All kind of that. Yeah. The easy that is not easy solution at all is saying, oh, so I have this kind of object, and this kind of object can just be manipulated by these 5 peers. And the thing is, then you have a centralized network. In the sense that it's decentralized, that everyone knows of this and all that, but that object can only be controlled by 5 people, which is centralized in its sense. Yeah. So the thing is, the OS, you have that solution. We can think about other kinds of solutions. The thing is, open problems. We need to do lots of research on top of them, and that's a big problem that always happens. Yeah, in the OS.
So what would you say is the hardest problem right now that you're facing?
Making everything work.
Okay.
Because actually we have lots of stuff that, so we are building most of the things from ground up. Peer-to-peer messaging, most of it is abstracted because of P2P, which is a super awesome tool. Sometimes it fails, but it's a super awesome tool nevertheless. The thing is, we are starting to build lots of stuff, and currently we are packed on building the stuff and researching on how to do better stuff sometimes, and that's currently our limitations. The thing is, as soon as we have something that is way more stable, then we start thinking about lots of other problems like DDoS.
Are you aware of that? I forgot the name. P2Panda.
P2Panda?
Yeah. They are doing similar things.
Yeah.
You know that.
He can talk way more about P2Panda, but we are aware of those, yeah. No more questions? So I'll be staying here for a bit more also. We also have some people here from Topology, so you can just ask any questions if you want and after. And thank you so much.
Yeah.